AP Calculus, section 7.3, page 8. For this page, you'll notice we have the same basic area shape region here, but the volumes are going to be different because our cross sections are different. We're not going to get circles this time. The first one, we have cross sections that are squares with bases in the XY plane. This paper is the XY plane. Here's our squares stacked together, and what happens is they're sitting like this. So when I cross section through, each time I cross section through, the base of that square is extending across this circle here. So that's sitting just like that. Actually, it's probably over a little farther, right like there. And hopefully you can see those cross sections are squares. If we go to draw this then, I always like to draw in my cross section. I'm running perpendicular to the x-axis. Here's my cross section right here. And that cross section is a square. That's a square whose base, so this was sitting like this, that piece right here, that base is that bottom piece right here. So this distance. Alright, now to find the volume. The volume, we're going to have to add up a bunch of squares times the thickness. Formula for area of a square is its side squared. Thickness here, we already can see that, that's a dx thickness. But now we need to figure out how long is this side right here. Alright, that's this length right there. This much is y. So this whole length here is 2y. So 2y quantity squared times dx. Alright, that 2 squared, so we're looking at 4y squared times dx. But y was square root of 1 minus x squared. We're going to square that times our thickness dx. Bounds, again, -1 to 1, or we can double it and just go 0 to 1. So let's do that. We'll have 4 times 2, 0 to 1 of 1 minus x squared squared dx. Oops, not 1 minus x squared squared, just 1 minus x squared. I already squared it in the last one when I got rid of the square root. My mistake, I'm sorry. Come on, get out of there. There we go. Okay, now, anti-differentiating through this. Didn't we do this just a little bit ago? This 1 minus x squared from 0 to 1? I think that came out to be 2/3. And 4 times 2, 8, so 16/3. Look, there's no pi in this. There's no pi because our slices are not circles anymore. Pi is only going to show up when we've got circles going on. No circles. Okay, now look at this next one. The cross sections are still squares, but the diagonal is in the XY plane. So instead of the squares sitting like this with a side in the XY plane, this diagonal is going through the XY plane. Now I can't go through the page, but if I had something like this, so there's kind of half of that square, and I've cut it so that it's standing here. Now you kind of have to imagine that the other side of the square is underneath the paper, going down underneath the paper. There's the diagonal of a square right here. The diagonal is sitting in that XY plane like that. Here's my cross section again. And that cross section is again a square. I'm just using this to trace. But this time, that cross section is not this bottom piece right down here. That cross section is this piece. It's that diagonal. That length, just like it was up here, is 2y. Cross section is a square. So we're still going to find volume by adding up a bunch of squares. Which is still a bunch of side squared. Thickness is dx. Now you have to remember your geometry and your 45, 45, 90s, because I have to go backwards from this 45, 45, 90, from the hypotenuse back to a leg. And to get from a hypotenuse back to a leg, you have to divide by the square root of 2. So 2y divided by the square root of 2 is 2 square root 2 over 2, or just square root 2 times y. That's your side length. Squaring this out, this is 2y squared dx, pulling that 2 out front, and then y squared is, we know by now, 1 minus x squared dx. Bounds, same idea because we're still slicing, same starting point, same ending point, so let's go from 0 to 1 and double this. So we have 4 times this integral from 0 to 1 of a 1 minus x squared dx, and this was 2/3, so we have 4 times 2/3, or 8/3. These are kind of running all over each other. I'm just going to try and separate them. Alright, last one here. Cross sections are equilateral triangles with bases in the XY plane. Equilateral triangles with bases in the XY plane. Alright, I am sorry I did not have any equilateral triangles with me, but I've got some other triangles that you can imagine. Hopefully, here's some triangles sitting this way. Those are equilateral triangles. You have to imagine equilateral triangles. I'm sorry, it's the best I got right now. Standing up this way, so cross section here, cross section is an equilateral triangle. Where the base is sitting right in here. That length is 2y. And all goes back to this distance is y, so all of that whole orange piece is 2y. You have a couple of options here with the equilateral triangles. You can remember from geometry that the equation for an equilateral triangle is side squared square root 3 over 4, which then the square root 3 over 4 can come out. Side squared, that would be a 2y squared times dx. Four comes out, takes out this one out here. Square root 3 y squared, we already know is 1 minus x squared. And then bounds, let's make this again 0 to 1 and double it, which this is all going to come out to be 4 square root 3 over 3. If you do not remember that formula from geometry, the equilateral area for an equilateral triangle, then you have to go back to 1/2 base times height, where this is a 30, 60, 90. And this length down here, y. This is 2y. This is square root 3 times y. And then 1/2 base 2y times height, y square root 3, and then work through and you should end up with the same thing. Alrighty. One more complicated one on the next page. We'll do elements of area that instead of being dx slices, they'll be dy slices. We'll take a look at those on the next page.